Okay, you're given this function and you're asking some questions about how to determine the zeros and behavior, etc. Sure, this is intended to be an equal sign, not a plus sign. So let's see what's happening by looking at a graph. Here's the graph of the function, this red curve. And here's a table of some of the values. And I'll also note that it looks like the roots are at 1 and 3. So there's only 2 roots. And it looks like when x is sort of negative or getting bigger in the negative direction or in the positive direction, the y values are getting really big. We actually call that end behavior up, up. And we'll see how to determine that a little bit later. Here on board 2, we have what's called the rational root theorem. As long as the function has integer coefficients, that's these guys, along with the constant term, any rational roots of that function have to be of the form c over d, where c is a factor of the constant term, and d is a factor of the leading coefficient, assuming we've written this in descending order. Okay, so our set of possible c values are factors of 15. That's plus or minus 15, plus or minus 5, plus or minus 3, plus or minus 1. The factors of the leading coefficient, which is a 1, are plus or minus 1. So if we want to form the set of all rational zeros, we put all these c's over all these d's. So this is actually the set of possible rational roots. Before we see how to use synthetic division to identify those roots, let's look here at the Descartes' rule of signs. This says that if f of x is a polynomial with real coefficients, we have all integer coefficients, and a non-zero constant term, which is true about our function, the number of positive real zeros is either equal to the number of variations of sign in f of x. Well, what do you mean by variations of sign? Well, here we went, the leading coefficient is positive, then we went to negative, then we went to positive, then we went to negative, then we went to positive. So there's actually 1, 2, 3, 4 sign changes. What Descartes' rule of signs says is that there is either 4 positive roots, or we're less than that number by an even integer. So there could be 2 positive roots or 0 positive roots. If I find f of the opposite of x, you can see how I put negative x in for x, and then when I raise to the even power, the negatives become positive. There are 0 sign changes. So that means there's 0 negative roots for this function. So if we go back to board 3, that means it doesn't make any sense to test the negative numbers. So the numbers we're looking at as possible rational roots are 15, 5, 3, and 1. And it's always easy to check for 1. You just write down all the leading coefficients. 1 minus 6 plus 16 minus 26 plus 15 is indeed 0. So 1 is a root. Now, how do we find the other roots? Well, one way to do it is to use synthetic division. So the coefficients of the original function look like this. And after you've done some synthetic division, you can just use a table of values out here. But until you get good at it, do it this way. Drop the leading coefficient. We put the number we're checking to see if we get a remainder of 0. In this case is 1. We know we're going to get a remainder of 0. But 1 times 1 is 1. Add negative 5. Multiply and add. 1 times negative 5 is negative 5. Add 11. 1 times 11, 11. Add. 1 times negative 15 is negative 15. Add. Remainder 0 means indeed 1 is a root, which we expected all along. Okay. Now, why did I do that? Because now we have f of x equals, if 1 is a root, x minus 1 is a factor. And these are the coefficients of the residual polynomial. If we did long polynomial division, we would get x cubed minus 5x squared plus 11x minus 15. And now we would do the same thing that we did for the original function for this polynomial to see if there's any zeros. And the numbers we would check, again, we don't need it to check any negative numbers, but we could check 1 again if we wanted to. We could check 5, 3, and 15. And if you do synthetic division with 3, I won't show it all. You'll find you get a remainder of 0. Okay, so 1 and 3 are the roots. I've already looked at this page. So if the roots are 1 and 3, one way to find out where the function is positive and where it's negative is to put the roots on a little number line and then find the value of the function in each of the intervals. So if you put 0 in for x, you get an answer of 15. That's actually the y-intercept. The function is positive everywhere to the left of this root. If I pick a number between 1 and 3, I get a negative number, negative 5 for f of 2. So the function is negative for all values between 1 and 3. And to the right of 3, for example, f of 4 was 39, so plus. And I'll let you set up interval notation to show those values. And finally, how do you tell what the end behavior is? When the leading term has an even degree, that is an even exponent, the behavior will either be up, up, or down, down. And which it is depends on the coefficient. If the coefficient is positive, like a positive 1 here, that means we're going to get bigger and bigger positive numbers in both directions. So if I put like negative 20 in here, negative 20 to the 4th is still a positive number. Times this positive 1, it's just going to get bigger and bigger to the left and to the right. That leading term dominates all these in the end. If this had been a negative number in front, behavior would have been down, down. Okay, there you go. Hope that helped. Kind of a long video. Pause it. Take some notes. If you have any questions, post a comment.